This is the short talk for PyMM, Heterogeneous Memory Programming for Python Data Science. My name is Daniel Waddington. PyMM, Python Managed Memory. This is an exploratory project to look at heterogeneous memory integration into the Python programming environment. We're specifically positioning this for the emergence of CXL attached memory and other persistent memory technologies. PyMM provides Python libraries that make integration of different types of memory extremely easy. Currently, we support local DRAM, FileMem mapped DRAM, and Intel Optane persistent memory. PyMM is based around the concept of a shelf, which is a collection of variables that are associated with a specific set of memory resources. Our current focus is on data science and data science programmers, and we're currently testing with basic Python, NumPy and PyTorch tensor types. Finally, we use interface conformance and subtyping to make shelf variables look like and feel like their main memory counterparts. The rest of this talk we're going to have a demonstration. Okay, let's see PyMM in action. So here we're going to use a Jupyter notebook with Python 3.9. First thing we're going to do is import the PyMM module. The PyMM module provides a number of abstractions and capabilities, including the key abstraction, which is the shelf. The shelf is the abstraction that basically collects variables together and assigns them to a specific type of memory. So let's see that in action. But before we do that, let's load some libraries and some display processing from a SkyKit image. So the next line we're going to actually create a shelf. The shelf variable will be called image example, and it will have a size of 32 megabytes and a persistent memory path of /mount PMEM. The last parameter here is just a simplifier for enforcing a new shelf to be created and erasing existing shelves. Once I've created a shelf, I can then see what's on the shelf using shelf.items. As you can see, it's currently empty. So let's put some data on it. Data.coins generates a NumPy image. Let's assign that to test image on the shelf. If we relook at the items, we can now see that there is test image. And in fact, we can use the shelf variable test image directly in anything that expects to see an ND array. So let's display the image using the display function. We can create other variables on the shelf alongside our test image. So let's try creating a new image that performs segmentation using the original image shelf.testImage. And again, we can display the result. Okay, for the second part of the demonstration, we're going to look at shelf recovery and how we get the objects back off the shelf once the program has been restarted. So again, we will start by loading the PyMM library, as well as some of our functional image processing libraries. This time we're going to open the shelf with a shelf constructor, passing again the same name as before, image example, as well as the persistent memory path. But however, note this time we're not passing the size variable because we're going to open an existing shelf. When the shelf gets opened, the variables that exist on the shelf are made available through the shelf structure. So here you can see that two values, segmented test image and test image, have been made available. And we can confirm that with the shelf.items attribute. We can also look at how much memory we've used from our original 32 megabytes of persistent memory resources using the shelf.getPercentUsed. So here you can see we've used 19% of the resources. And we can also access the data without pickling or deserialization. We simply access the variable as a member of the shelf. So here I'm going to display the test image. We can also do in-place modifications to data. So for instance, here times 2 will multiply each element of the matrix by 2. Note that after the execution, this was considered a single function, single variable atomic. So once the function calls are being executed, the persistent memory is made sure to be flushed. As well as performing the default single variable transactions, we can also create groups of variables within a single transaction. So here you can see shelf.txBegin, and we're passing in the two variables that we have on the shelf, test image and segmented test image. These will both be collected into the same transaction. So now we're going to perform a loop which performs in-place write modifications. You'll see that we don't see the persisting memory logging in each iteration of the loop. And this is because their writes are amortized together. To explicitly finish the transaction, we call shelf.txend, and then we'll see that the persistent memory is flushed. Thank you for watching the presentation. I hope you enjoyed it. Please check us out on github.com.